Welcome to this short video on doing simulations of conducted EMI using RidleyWorks. So let's get started.
Click on Specifications to start your design.
You can see here we have input specifications of 360 to 380 volts, output voltage of 12 volts and 20 amps, and a frequency of 100 kilohertz. This input spec is what you might get as the output of a power factor correction circuit, or it could be another application with that kind of range. So let's look at our simulation of the converter. We can see here's the inductor current, here's the startup with the converter just getting going. See it hits a peak of around 27 amps or so. We continue to get us into steady state. And then we can see we have about a 30-40% ripple on the converter. Okay, one of the biggest problems when you're designing power converters is filtering it so you can meet the EMI specifications. So let's go to our tools icon here, and we can turn on the input filter design inside RidleyWorks. Click on the filter. Here it is, a filter here you can see has already been designed. Everybody has their own methodology for doing that. We have a default version, but we're always working on that. But here we see you have actually a fifth order filter, an LC, and then a second L with two different values of C on the output. That would represent the bulk capacitor that you use, and then a higher frequency bypass cap across the filter. Inside RidleyWorks, we do two things. Firstly, we check the classic Middleburg interaction of impedances. We want to make sure that the output impedance of the filter, the green curve for us because we're using a two-stage, we want to make sure this impedance doesn't get anywhere near the input impedance of the power supply. And here you can see we have a really good separation. And by doing that, we make sure that the filter is not going to create any stability issues. In the curve below, you can see the power of having a two-stage filter. Out at around 100 kilohertz, it's achieving about minus 80 dB attenuation versus, of course, the one-stage filter, which is about 40 dB worse than that. So it's a very powerful thing to use two-stage filters in your converters when you're trying to meet very low noise requirements. So we don't try to predict the EMI spectrum inside RidleyWorks. LTspice is actually much better at doing that. So what we want to do now is go from this converter running closed loop to LTspice.
LTspice schematics.
And there you go. That's it. It exports that schematic with all the values of LTspice, of the filter, into LTspice. Now we come into LTspice. And always we open up the same name file, the transient file. And here we can see our two-switch forward converter, and the input filter is shown on the input side here. So all the values are automatically carried across into LTspice. Let's run a quick simulation here. And then we'll look at the output current, which is what we looked at inside RidleyWorks. And there you can see that same output current inside LTspice. Runs a little bit slower, but it's really a pretty good simulation speed. I'm not too worried about how fast LTspice goes. It's doing a good job. Okay. Now what we want to do, remember our intent was to try and measure the EMI of this converter. So to do that, we have to do what we have to do in the lab, which is insert a LISN. That's a line impedance stabilization network. So let's move the converter elements on the input a little bit. Sorry, clicked on the wrong thing there. We're going to make space for that LISN to come in. So we'll move that part of the converter to the left. And now we'll go look for the LISN component. And this comes with RidleyWorks. When you buy this, it automatically puts the LISN in your circuit folder of LTspice. We use LTspice 24. It's much faster and much more predictable, we find. So let's place that LISN. Here it is. We're going to put it on the input side. We only need one of those, so there we go. Now we're going to hook it up. Let's zoom in a little bit on this schematic. Let's go full screen here. You see our LISN now. So we'll connect a wire from the input to the voltage source. We'll connect another wire from the output to the input of the converter. And then the return lead goes down here. And it connects to the schematic, and of course we've got to connect that to ground as well. Okay. And then on the output of the LISN, there is a test port right here. So we want to actually load that with a 50 ohm resistor. So we'll put a 50 ohm resistor in the circuit. Let's edit the value to 50. Okay. And we'll hook that up to the analyzer. This will be a BNC output on your analyzer. And normally it goes to a 50 ohm input in a spectrum analyzer, which you should have in the lab. Okay. Now we're ready. And we're going to run this circuit. Let's click run. And you can see the converter is running quite happily as before. Doesn't seem to worry too much about all the components inside the LISN. And what we want to actually look at is the voltage across this resistor. That's our test voltage. And you can see some things going on here. There's some ringing at the beginning. We want to get it into steady state before we start collecting any noise data. So we don't want to be during this transient region right here. So let's look at our command statement. So we want to do a transient. Okay, and we don't want to collect any data until we've been running for 10 milliseconds to let all those transients die out. And then we'll run the simulation. We have to run it for a longer time than that 10 milliseconds. We'll run that for 20 milliseconds. Okay. Now sweep again. Run the simulation again. And you can see the counter of time at the bottom there. It's 6, 7, 8, 9, 10 milliseconds. Then it starts outputting the data for you. So it's important to know how to edit the LTspice transient statement to get the data that you want. Okay, we don't need to see the current anymore. So let's go get rid of that. And now we're just looking at the voltage coming out of the analyzer. And you see it's quite small. It's in the range of plus or minus 600 microvolts. But in terms of passing EMI, you know, everything is measured in dB microvolts. And we're only allowed to generate a very small amount of noise. And that's the big problem with switching converters. They're terribly noisy things, even with the filter in place. You can see a lot of noise here. So now we don't want to look at the time domain waveform. We want to do what the spectrum analyzer would do. So we click on View, Fast Fourier Transform. And this is node 12 that we're looking at. And there is our classic noise spectrum. So you can see the big spike here at 100 kilohertz, 300 kilohertz, 500 kilohertz, and so on. And then you can see another band of noise bumping up here. Always happens in converters like this, where you get these high frequency components in the megahertz range. Usually they're the worst ones to get rid of, quite honestly. Now we don't actually want to plot this because our scale here is in dB volts. And the normal range we plot for EMI is dB microvolts. So let's edit this. Multiplied by 1 million. Okay. And all that does, of course, is shift the axis on the left by 120 dB, actually. All right. So now you can see these spikes appearing here, and your job now is to see, does this fall below the specifications that you've got to meet for conducted EMI? So at 100 kilohertz here, we can see we are at 52 dB. So that's 52 dB microvolts, which I think is below the limits. And if you put the curve on top of this, you'll be able to see that we've probably passed the conducted differential mode EMI here. Let's do a little experiment here. Let's run that again where we short out the filter. So we'll put the short across this filter right here, and we'll rerun that waveform. Again, it's going to collect data for 10 milliseconds, or it's going to ignore data for 10 milliseconds, then it'll start collecting, and there's the plot. Okay. And now we want to do, click on here, view the FFT of that. And now we see at, oops, sorry, I want to go to microvolts again, times 1, 1, 2, 3, 4, 5, 6. Okay. So here you can see we've got about 165 dB microvolts in this case. And the previous sweep we did was just 50 dB microvolts. So this represents the attenuation of the input filter that's going on. So this is the previous version, and this is the new version. Obviously on different scales. So we were 170 before, and now we're around 50. So we're attenuating greatly by having that filter in place. So now you can see the effect of the filter. Does this mean you're going to pass EMI first time? No, because there's going to be common mode effects as well. But if you don't pass this condition with the differential mode, then there's no hope that you're going to pass the actual measurement in the lab, which is going to add more noise from the common mode. So you see how this gets you started in the filter design, and I hope that this proves really helpful to you. So there you go. There's everything in the filter design, and I hope you enjoy using this feature of RidleyWorks.